Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be talking about an asymmetric evolutionary game. My name is Rick, and my co-teacher, who originally prepared these notes, is Christoph. Okay, let's briefly outline what we're going to do today. Obviously, we're going to talk about an asymmetric game. We'll choose one from the set that we've looked at in the past. Then we'll go through some of the economic solution concepts, namely the Nash equilibrium and Pareto optima. And we'll do that just very briefly, just to get a sense of what it looks like in a classical perspective before we move on to the evolutionary perspective. And then we will look at it through the lens of evolution. And the question that we'll mainly be addressing is how to handle this case where there's asymmetry. We've previously looked at symmetric games using evolutionary game theory. Now we want to go beyond that. And we'll be looking in particular at two approaches, either separating out the populations or randomly assigning roles. That might not make much sense at this point, but once you see what kind of the issue is, then you should be able to see why we need to do these two possible things. And which choice we make when we're doing this should really be driven by the system that we're looking at. It should tell us, what is the right approach when we look at these asymmetric games. So let's take an asymmetric game as an example. So we've studied a few asymmetric games in an economic perspective, from an economic perspective. For example, we've looked at the ultimatum game. We've also looked at matching pennies, although when we played it in class, it was matching fingers. We've done Sotto versus Blotto, and we briefly looked at Battle of the Sexes. So let's look at the ultimatum game again. But let's look at it from the perspective of two players making simultaneous decisions. Just to remind you, the ultimatum game, we had two players, a proposer and a responder, and this was a sequential game. So the proposer went first, then the responder went. The proposer could choose to make a high offer or a low offer, and the responder could accept high only or accept all offers in either case. And the offer values were such that a low offer is more than nothing, but not as much as a high offer, and a high offer is less than everything. So 0 is less than L, is less than H, is less than 1. And under these conditions, the payoffs are 1 minus H for the proposer and H for the responder if the proposer makes a high offer and the responder accepts high only. Likewise, if the responder accepts all offers, if the proposer makes a low offer and the responder accepts all, then there's the payout, 1 minus L to the proposer and L to the responder. And if the proposer makes a low offer, but the responder only accepts high offers, then nobody gets anything. And we saw that if we look at the proposer or the responder, we can work out what the where the SPE is. There's indifference in the top branch, but in the bottom branch, the responder prefers accept all. So that means the proposer can either earn 1 minus H or 1 minus L. You would prefer 1 minus L because he's losing less. He's only losing L out of the total. So the proposer will prefer the bottom branch. And there we go. That means that the outcome low and offer low and accept all is the SPE. That's the extended form of the game with our decision tree, but let's consider the case where the responder doesn't know what the proposer is going to do, and we can indicate that with a little bubble around the responder's choices. Effectively now, since the responder is ignorant of the proposer's strategy, it's effectively a simultaneous decision, or we could say it's a simultaneous game. And since it's a simultaneous game, we can represent it with a payoff matrix. In other words, it becomes a normal form game. So we have a responder, which can accept high only or all, and we have a proposer that can make a high offer or a low offer. And the payoffs in this case are just given by 1 minus H, H, 1 minus H, H, 1 minus L, L, and 0, 0 if they can't agree. So let's draw our preference arrows and figure out where the important outcomes are using our classical or economic solution concepts. So the proposer would prefer 1 minus H over 0, but it would like 1 minus L even more than that. The responder is indifferent to the two options in the top row, but in the bottom row we would prefer L over nothing. So from that we see that the bottom right is a strict Nash equilibrium. We also see that the top left is a weak Nash equilibrium. And there are three outcomes that are Pareto optima. Okay, so we see here that there are two Nash equilibrium. One of them is strict. Both of them are also Pareto optima, so there's no social dilemma in this game. Not an obvious one anyways. One question we might ask is there a mixed Nash equilibrium? And I think we better check that. So far we've figured out the pure Nash equilibria, but there could still be a mixed one. To figure this out, we'll use the technique we used when deriving mixed Nash equilibria, and the third technique we used was the endpoints shortcut. And how that worked was that each player chose a mixed strategy that made the other player indifferent to the extreme strategies he could choose. So let's make that a little bit clearer. The proposer has some probability p of choosing high and 1 minus p of choosing low. The responder has a probability q of choosing high only and 1 minus q of choosing all. And now, what can the proposer do? They can choose this special value of p star, to make the responder indifferent. So let's work out what the payoffs to the responder are under these conditions. So let's call it utility of the responder. If the responder chooses high only, is h with probability p star. Otherwise, it's 0 with probability 1 minus p star. And what we're really talking about here is this high only strategy, and the proposer has a probability of p of choosing, or p star now, of choosing high, and 1 minus p star of choosing low. So the responder can either get this h or 0, and these are the probabilities of those choices, those outcomes. That can be written, of course, a little bit simpler. It's just h times p star. Let's look at the other limit. The utility of the responder if they should choose all. Exact same reasoning. So it becomes h times p star plus, now it's l times 1 minus p star. And this criteria here, choosing p star to make the responder indifferent, means equating these two things to each other. So we want to set the utility of the responder if he chooses high only to be the same as the utility of the responder if he accepts all, and we conclude that p star has to be equal to 1. Let's do the same reasoning for the responder. The responder is going to choose q star to make the proposer indifferent. Let's work out the utilities of the pure strategies for the proposer. The proposer can choose a high offer, and if the responder accepts high only, which occurs with probability q star, then the proposer gets 1 minus h with probability q star. On the other hand, you could get 1 minus h with probability 1 minus q star. So basically what we're saying is that the proposer is going to get 1 minus h if he chooses high. And just to look that over, what we're talking about here now is the high strategy, and what will the proposer get if the responder plays high only, which occurs with probability q star, or plays all, which occurs with probability 1 minus q star. And in either case, the proposer is going to get 1 minus h. And for comparison, we need to look at the other limit. If the proposer chooses low, then there's a q star chance that he'll get 0, and a 1 minus q star chance that he'll get 1 minus L. Again, we set those two utilities equal to each other, and we get that Q star is going to be equal to, well, it'll be 1 minus H over 1 minus L, and I can see that simplifies to H minus L over 1 minus L. And of course, we need to check, is this really a probability? So is it bigger than 0? Well, or greater than or equal to 0? As long as H is bigger than L, then it is, yeah. And of course, 1 is bigger than L as well. And both of those conditions are already true, so Q star has to be bigger than 0. The second check is it smaller than or equal to 1? And as long as H is less than 1, then that's true as well, because then the numerator will be less than the denominator. So check. This is a probability. So our classical or economic solutions, which means outcomes or strategy pairs that are likely to occur, consist of two pure Nash equilibria, a weak one at high only, that's the strategy pair, and a strict one at low, that means make a low offer, and accept all. And on top of that, we have one mixed, any, and it occurs at p star q star equals 1 h minus L over 1 minus L. Which outcome is going to occur? We can't really say. You can figure out what the payoffs are for all three of these if you like. What you'll find is that sometimes it's the one player gets a higher payoff, and sometimes the other player gets a higher payoff. So that means there's still some tension in this game, because they might agree these are the outcomes that are going to happen, or they have to choose from, that they're likely to choose from. But there's still the dilemma of choosing which one, and how is that going to occur? And so there's still some interesting tension there. Okay, now we can move on to thinking about this from an evolutionary perspective. And the question we're interested in is, how do we handle asymmetry in a game using an evolutionary approach? So what we've done so far is we've looked at the replicator equation, which we've written as dx dt is equal to x times 1 minus x times fa minus fb, or we've also written it as x times fa minus f bar. Those are the two forms of replicator we've used, where a and b are the available strategies or types in the population, and x is the frequency of a's. In this notation, the fitness, fa and fb, equals the fitness, which is just the average payoff after sampling many pairs of individual players to play the game. Really, we're talking about the limit of every player versus every other player. So you might think of this as if we have a player, and then maybe we have another player, and a few players. So we start randomly sampling these players, and maybe this one plays against that one, and maybe that one plays against that one, and maybe this one plays against that one, and we could have that one playing against that one, and that one, maybe between those, and there could be something there. And if we keep doing that, eventually every player has played every other player, and we get the average of all of those pairings to get the payoffs for each of the players. So it's just a matter of drawing two at a time and having them play against each other. You could think of it as sampling with replacement in statistics terms. So how do we handle that if there are separate roles or an asymmetry in the game? For example, we could have a proposer and a separate responder, and they're not the same as each other. So if we had this situation, we might have two different types. And if we did the same kind of thing, we might have pairings between these two guys and maybe these guys and these guys. That would all be fine. But what does it mean when we try to create a pairing like this between two proposers? That doesn't make any sense. They can't play the game together. So these pairings are fine, but this pairing is not. And we need to decide what to do about that. So there are two kind of obvious solutions to this. We could have two separate populations, and we only allow games to be played across populations, not within. So we could have all our blue types in one population and all our red triangles in another population. And we set up so we only allow interactions or games to be played across. That would take care of the problem. The other approach would be to randomly assign a role. To do that, if I'm going to be randomly assigned a role of a proposer or a responder, I had better know what strategy I'm going to choose under either condition. So I need a strategy for whether I'm a proposer, and I need another strategy for if I'm a responder. So I need my strategy if I'm a square and if I'm a triangle. So I need to be a house. And if we have a population of these guys that have both strategies defined for them, then they can interact with each other. And sometimes each of these players will be playing as a proposer, and sometimes they'll be playing as a responder. So this proposer could play against that responder, and on the other hand, that first player could play as a responder against the other guy as a proposer. And I think that's all the possible interactions that could happen between these guys. So let's look at these two possibilities in a little bit more depth. This isn't something that you should expect to see on the exam. The details of this kind of analysis, you should be able to understand it and see how it works in general. But it's more something that you will be expected to be able to do throughout your project, for example. This might be one of the kinds of approaches you could take to kind of extend the model beyond that you're looking at beyond the simple kind of symmetric 2x2 case. And this would be one way to kind of help demonstrate your mastery of game theory. So let's look at the case of separate populations in a little bit more depth. So as we mentioned, in this case, the role of the players is fixed, and they only play against the other population. So if you're looking for a kind of an example, it could be something like courtship or mating between males and females. So I chose that example because it's clearly all within a species. And if you think about it from a strictly an evolutionary perspective, you can see that if we think of the number of offspring as the payoff or the fitness, then mating between males and females can potentially produce offspring. Matings between males and males will not, and females will not, without reproductive assistance. So let's see how this applies to the ultimatum game. So we've got two populations, a proposer population, and in that population there are two types, the high offer types or the low offer types. And let's define X to be the frequency of the high offer type. On the other hand, there's the responder population, and there's a high only or accept all, and let's call the frequency of high only Y. The replicator equation still holds, but now there are two replicator equations. We have dx dt is equal to x times 1 minus x times, let's call it fh minus fl. That's going to be the fitness of the high offers and minus the fitness of the low offers. And for y, we have dy dt is equal to y times 1 minus y times f, let's call it ho minus f, I'll just say all. So ho is high only. Now what happens here is the payoffs depend on who you're playing against, so it depends on the other population. Let's see what that looks like. So for the proposers, the fitness of the high offer type, on average is, well, it depends who you're playing against. There's a probability Y of playing against high only, in which case the proposer will get 1 minus H, and there's a probability 1 minus Y of playing against accept all, which will also give 1 minus H. So really, the fitness of the high offer type is just 1 minus H, and it doesn't depend on the frequency of the responders of what Y is. On the other hand, let's look at the fitness of the low offer type. If they go up against high only, then they get 0. If they go up against an accept all, then they get 1 minus L. So this is the fitness of the high type, and here we have the fitness of the low type. Go ahead and work out the same thing for the responder. What would the fitness of each of its types be, and how would it depend on the other population? You should pause the video now, and when you're ready, resume it. Okay, here are the results, at least the ones I got. Okay, we can go further. Now that we know this, we can use a simple graphical technique to draw the phase plane, which means we can work out the equilibria and their stabilities, very much like we did in the one-dimensional case where we first introduced evolutionary game theory. But now we're doing it in 2 dimensions. There's an x dimension and a y dimension. And so that adds a little bit of a twist. And you should try to understand what I'm doing. And if you want to go along these same lines, then come talk to me and we can work through some of the math together. You don't have to do it all on your own. Although I will say, if you've taken models in science, ISCI 422, then this should look familiar to you. So the basic idea of using the phase plane technique is that we draw 2 axes, x and y, and we try to figure out where one or the other of the rate equations is 0, which means that either x is not changing or y is not changing. So here we have x equals 0, here we have x equals 1, this is y equals 0, and up here we have y equals 1. And we want to know, when is it that x is constant or y is constant? So let's consider the case where dx dt is 0. So that means x is constant. That can happen when x is 0, or when 1 minus x is 0, meaning x equals 1, or when fh equals fl. The case x equals 0 is right here. The case x equals 1 is over here. So those are places where dx dt is equal to 0. The third condition where that's true is for some constant value of y, and that would be where fh equals fl. And you can check for yourself that is means that y is a constant. We can also look for where dy dt is equal to 0. And one of those conditions is that y itself is equal to 0 or y is equal to 1. And the third condition is when fho is equal to f_all, which you can check for yourself, just comes down to the case x equals 1. Okay, now, wherever they don't cross zero, these rate equations, they have to be either increasing or decreasing. And if you look at those rate equations carefully, you'll see that dx dt is negative when we're below this value of y, this threshold value, where it crosses zero. So in this range, we have to have x decreasing. This is very much similar to the argument we made when we first derived evolutionary game theory. On the other hand, when we cross that thick blue line, then x starts increasing, or dx dt is positive. So we would be moving in that direction. On the other hand, y is always, within this square, is always changing in the same direction. It's always decreasing. So it's decreasing in this region, and it's still decreasing in this region. And so the net direction of motion in each of these regions is the net direction of motion in these regions is the vector sum of these directions. So in the top region, it's down and to the right, and in the bottom region, it's down and to the left. There's also motion in the areas where only one of these derivatives is zero. So if x isn't changing, then y can still be changing. And what we see is as we're crossing this line, we're moving straight downwards. Also, along this left axis, we would be moving downward. Along the top, we would be moving just to the right. And on the bottom, we would be moving just to the left. And you can work these out for yourself, and I can help you with those if you need a hand. Now, what about places where the two derivatives both are zero? By definition, those are equilibria. So wherever these two lines cross each other, the red and the blue, that's an equilibrium. That's an equilibrium. We've got an equilibrium here. Oh, wait, there's something kind of special going on here. Because, sure, these all cross each other. But along this axis here, we've got a line of all red and all blue. So every point on this entire line is an equilibrium. I'll just draw a bunch of circles to make that point. Okay, this is a really, I find it a really easy way to quickly visualize what's going on in a system. It's something you can do, on a scrap of paper and quickly understand what's going on in a two-dimensional dynamical system. It takes a little bit of practice and getting used to, but let me show you what it can tell you. Once we have this phase plane, we can draw some sample trajectories to get a sense of the whole flow of the system. Let's pick a random point in the top half here. And think about what would happen to this if it was moving with these kind of vector directions pushing it along. So initially we'd be moving kind of down and to the right. As we got closer to this line, we'd have to be moving more and more vertical because the flow becomes vertical like this. And then as we moved into the bottom region, we'd have to turn around and start moving down and to the left. So our trajectory would take us something like this. And the same has to be true for wherever we start in the top region, with a few kind of important exceptions. Because remember this line of equilibria. Where else have we got equilibria? There and there. So let's say we started way up here. We'd be doing the same thing. We'd move along to the right. But it seems to me there's a chance that would crash into the boundary here. And what would happen then? Each point on the boundary here is an equilibrium. So we just stay there. Except if we were actually talking about a real population, then we might not stay there. We might get kicked around a little bit because, there's going to be random births and deaths. And so, and there could be immigration, there could be emigration, there could be mutation. Things are always changing. So even if we're right on the boundary, there could still be the introduction of new individuals of a different type that would kick us out off of that boundary. And so we could be kicked, let's say we zoom in on this boundary, we could be kicked up in that direction or down in that direction or out back out into the interior of the square. And as that happened, if we were kicked up or down, we just move to a new equilibrium and just stay there until we were kicked to another one yet. So if we started here, we could get kicked up here, we might move around a little bit more, and the random kicks would kind of bounce us around a little bit with no real trend driving us one way or another. But I can see that if we got kicked out into the interior again, then we'd be subject to this kind of trajectory again. So we'd be kicked out and then we'd be driven down in this direction. And so we'd tend to come back to the boundary, but a little bit below where we started. So the net result of this is that we'd slowly be driven, with some bouncing probably, down to here. And once we got into this region, then something else interesting will start to happen. Let me finish off this diagram if I can, before I talk about that. So I'm picturing this as kind of a a blow up of a tiny region here. And these are kind of what you might call perturbations that kick us around. Okay, so the rest of my argument was if we're down in this region on the boundary, then we might get kicked up and down still, but eventually we are probably going to get kicked out into the interior again. And when that happens, then we're going to be subject to trajectory that's pushing us down into the left. So we're no longer staying on the boundary. Instead, we'd expect to come down something like that. And so that gives us an overall sense of what would happen in our system. Without even solving any of these equations, I have a pretty good feeling for what the dynamics are. When there are many high-only responders, which means Y is large, then from this analysis, I expect an increase in the frequency of high offers or high offering proposers. And that makes sense. They'll tend to do better than the low offering proposers because those guys never get anything against these high only responders. But while that's happening, the frequency of accept all responders increases, meaning that Y decreases. And eventually we reach a point where the low proposer can thrive and take over. And that's the lower portion of the graph. And in the end, we really expect there just to be one stable equilibrium. And that's at the origin, which means we have a population of only low offers and accept all. And all of that we could see just from doing the phase plane analysis. As I said, this kind of analysis isn't something that you'd be expected to do in on an exam, but it is kind of the level that you could be expected to do if you want to do well on your project. Now let's talk about the other way of approaching this problem, and that would be to randomly assign roles. So when we're taking this approach, we have to remember that every player carries strategies for both roles. So I have a strategy for if I'm the proposer and another strategy for if I'm the responder. You might compare that or think about that in a kind of a biological framework as two separate genes with two alleles each. So we have then 4 types of individuals: the proposer and separately the responder strategies. And so we would have to specify both of these for every player. So let's say they could be like H for the proposer and HO, high only, for the responder. Or they could be H or high proposer and accept all, or they could be a low offering proposer and accept high only responder, or offer low and accept all. Now it's okay to let all of these 4 types play against each other. And what we can do is just toss a coin to assign roles. So this might be something more like biologically, I'm thinking. This might be not like males and females in a courting or a mating situation, because they can't change their roles. But here you can change your roles, and it's just luck that determines which role you get placed in. So it might be something like you find a valuable resource and you need to decide whether you're going to share it or not. Or the other player finds a resource and you need to decide whether you're going to fight for it or not. So it could be something like sharing lucky find. So which role you get placed in isn't up to you, and you just need to have a strategy that prepares you to act for whichever role you're placed in. But we're going to look at it again in terms of the ultimatum game. And so now we have 4 possible big strategies or types, and we need to work out what the payoffs are in all 4 of these cases. Let's work through a couple of them, and you'll see how it goes. So if I'm an HHO and I'm going up against an HHO, well, there's a 50% chance that I'm going to be the proposer, in which case I make a high offer, and the other player I know will accept because they accept high only. So I will get, in that case, 1 minus H. On the other hand, the same situation could arise, and I could be the responder, in which case I will accept. So in that case, I will get H. And the net result of that is that I will get a half if I go up against an HHO. And you can do the same reasoning for all of the other cases. This will also be a half. Here we get a half times 1 minus H. Can you see why that is? Work it through. Make sure you understand that. Okay, if I did the math right, this is the payoff matrix for all 4 types against all 4 other types. Notice that I've only written down the payoffs for the row players. Why is that? because this is a symmetric game. Now, once we have this, we can write down the replicator equation again. Now, we're talking about a case where there are 4 different types and not just 2 types. So it's a little bit more work. First, we would write down the fitness for all our types. So to get the fitness, we need to think about the frequencies of all 4 types in the population. So we could say that this is x1, maybe x2, x3, and x4. Those are the frequencies of the different types. And likewise, x1, x2, x3, and x4. And one detail to be aware of, we must have these frequencies add up to 1. Okay, with that, we can write down the fitness for an individual of type 1. Call that 1, 2, 3, and 4. Those are the types. So in the top row, we're figuring out the fitness of a type 1, and there's a chance x1 of going up against a type 1, in which case I would get fitness 1/2. Probability x2 of going up against a type 2, which would give me a payoff of a 1/2. x3 is probability of going up against a type 3, and the fitness would be 1/2, 1 minus h, and x4, 1/2, 1 minus h. Okay? You could do exactly the same thing for all the other fitnesses, and once you have that, then you can calculate the average fitness of the whole population, which is just the fitness of type 1 times the frequency of type 1 plus the rest of them. And that's all we need in order to figure out the replicator equations. Now, in this case, there's going to be 4 replicator equations, and each of them should have the same form. dx1 dt is equal to x1 times f1 minus f bar. We can't use the other form because that was specific to just having 2 types in a population. This is the more general form. And we'd continue that on, and then we'd have to work the math. And it can be a little tricky because things are getting kind of a little bit out of control here. So I think what we should do is not continue down this line of reasoning, but rather, if you're interested, you should come talk to us, me or Christoph. There are often shortcuts that you can use that make things much easier, but I'm not going to go into them now. There is a shortcut. Actually, I know of 2 shortcuts that can be applied in this case, but they're specific to this case. So they're not going to be generally very helpful to you because they won't help you solve other systems necessarily. The other approach that I used, having 2 separate populations and drawing a phase plane, all of that is very general and can be done for arbitrary payoff matrices. So that's a technique that you should be able to do. It will really depend on the details of the system that you come up with. So you might look at the model that you've come up with for your project and think about whether you want to do it this way. And it might be the right way, but we should have a look and see depending on the details that you get. Okay, so let's leave things there and just go over what we covered today. We looked at asymmetric games, in particular, the simultaneous version of the ultimatum game, and we found the Pareto optima and the pure and mixed Nash equilibria. Then we started thinking about evolutionary game theory, and how can we handle asymmetry in it. We came up with 2 answers. One is that we can use separate populations, and to analyze that, we used a technique called phase plane analysis, which is really just a 2-dimensional extension of what we did in the first derivation of evolutionary game theory. And we used that to find the equilibria and the general trends or the stabilities in the system. The second approach we looked at was to randomly assign roles. And in that case, we got a 4x4 symmetric game, which can be difficult. And if you're approaching it from this direction, you may need some help. Just come and talk to us and we'll see what we can do to help you out. As I've mentioned before, the choice of these 2 is not so much up to you, depending on how you set your system up. But if you're looking at a real system, it probably dictates whether it's fair to look at it from the perspective of 2 separate populations, or whether randomly assigned roles is the correct way to look at the game. So those are the approaches. You should understand or try to understand the phase plane analysis, and so you can maybe work through it yourself. And if you have questions, come talk to me, and I'll try to help you out. And we'll go from there. As I said before, And I just want to reiterate and emphasize, this is the kind of analysis or level of analysis that you might be looking to do in your project. It's not kind of the baseline level of an exam or anything like that. It goes beyond what you might be expected to do in an exam. But when you have plenty of time and you have lots of resources available to you, you should be able to do this kind of thing in kind of a extended period of time, like working on a project or a report. Okay, I think I've said enough about that. So that's all then for this lecture. Thanks for watching.